5 more minutes and then we should start. Okay, so let's start. About GNNs, I won't waste much time since it has already been taught. So I will give a quick review video. First thing is how to compute node embeddings. The second thing is how many types of graph neural networks are there. Then what are graph transformers, then what are knowledge graph reasoning embeddings, then what are generative model for graphs, and then what are graph databases, then GNNs plus LLMs, and then environmental applications. This is the syllabus which is given by this course. But what we are going to study is just 2-3 topics to start these topics. Okay. So generally, graph machine learning is done by this library called Geometric. Very innovative package and library from that. But nowadays people also use Torch, Geometric, and like Region and other stuff. Yeah, so we will start. You already know what are graphs and what is this, like what graphs represent. So like your events graph is how will you be booking a flight. The computer network is like how the computers are connected, disease pathways, and neural networks, multiple things. Databases are graphs as well. Relational graph deep learning is basically mapping databases to graphs and then learning over it. By the way, I should be audible. I hope so. I'm audible. Amazing. Just a second. Sorry. the basic coding stuff. I will directly jump to something known as how to build a graph. So a graph has nodes and edges, and whether a graph can be undirected or directed. Okay. Bipartite, what else? There are like different applications, so different type of tasks are there. Node level task is predicting what kind of mode it is. It's a customer, it's a shopkeeper, whatever it is. Then community level is what is this community coherent or not, or is this community relevant or not. Edge level is predicting whether this edge connects properly, these do not properly, or like at the graph level, whether this graph is suitable for some task or not. Node level, link level, graph level predictions, these are the two types of predictions. What is a node, what is a link, and what is a graph? These are the questions we ask. Node level tasks are classifying nodes to a category. Then characterize the structure and position of a node. Okay. Link prediction is adding missing links or adding links like new nodes to the existing nodes is also a kind of link prediction task, because assume the new node is also a part of a graph, but it is not like connected to any node, so you have to predict which node it will be connected to. Okay, so assume the recommendation system where link prediction is run. And then graph level tasks are just traffic prediction. We want to predict is the traffic heavy or not. So you model road network as a traffic, and then you model the time of arrival between two nodes. Drug discovery and other stuff. So this is all about the graphs and their applications. Now coming to node embeddings. So in traditional ML, you give some input graph, construct features from that graph, and then you learn an algorithm when you predict. But in graph representation learning, we don't do feature engineering, we learn the representations directly. So you take a node, okay, you should take a vector of the dimension for it, map nodes to an embedding space, similarity of embeddings between nodes indicate their similarity in the network. Okay, the nodes are close to each other. Because these embeddings are used for book prediction, mode classification, graph classification, detection, clustering, whatever node. So how are we computing node embeddings? So assume we have an undirected graph G, use the vertex, set, use the adjacency matrix, no extra features are given. The goal is to encode nodes for similarity in the embedding space or dot product and approximate the similarity in graph. So assume two nodes are connected and we assume their similarity is 1, directly connected, so we will try to bring the similarity to 1. So we encode U and encode V and bring the similarity close to 0. But we need to define the similarity in original network. Okay. Now let us exit over. So similarity in the embedding space is this thing, dot product. But it is very difficult to define similarity in the embedding space, like in the original graph. So what we do is, so we create encoder decoder architecture. We have an encoder that maps nodes from nodes that maps I think this is recording from this video. We define node similarity functions such as dot product. Then we define decoder that maps everything to the similarity scope. Okay. And optimize the parameters of encoders so that the similarity of UV in original network is similar to this thing. Encoder has predicted it to ZD, similarity function defines the similarity dot product. And this is basically the similarity from the dot product. Okay. Encoder is system embedding method. So what you do is you create an matrix Z. Okay, with each column has a node embedding. And you multiply V and you get multiply. Is like the position of the sector. Okay. So encoder decoder from the encoder is basically the node similarity. So basically we define node similarity. So this sounds ChatGPT. similarity assuming there is edge is equals to 1. So if an edge exists, the similarity is 1. If an edge does not exist, similarity is 0. So assume that thing, you can frame it that way. But there's another way, like if two nodes have like joined by one hop, so you assume the similarity is 2 and then you train it to be close to 2, and that's how you learn the embeddings. And you create a matrix, and basically this V vector is your just hold on a second. Hello? Hello? Anji? मैं काम करूँगा yes, sorry about that. Okay, so each column is a node embedding, and this is like we get a vector, so we can get a vector of node embedding, we get the final embedding because the others are 0. Okay. How do you define node similarity? So node similarity should be like if two nodes have similar embedding, if they are linked, shared neighbor, but have similar structural layers. Okay. So yeah. So today we are studying about the graphs and like how the graphs work actually. We are going to the problems of right now. Yeah. So if the nodes are similar, if they have like a shared link, if they are connected by edge, if they have common neighborhood, or if they have similar structural layers. So we now the thing is. Assuming this graph, this node and this node has just a common link, so you can take this similarity as 1. Then you subtract the number of common nodes, like you can add it like these graphs. So like if there are 4 common nodes, so you add 4, the similarity becomes 5. The greater the similarity, the better they are. So that's how you learn it. Okay. There are many methods like leapfrog, node2x, so we'll study them anyways. But we'll now study node similarity definition that uses random walks and how to optimize embeddings for such similarity models. Okay, so they are like unsupervised, self-supervised methods that do not utilize node labels or features. The goal is directly just to make the coordinate, so they have some other report is preserved. These embeddings are task independent because they are trained on the graph itself. Okay. So random walk approaches for node embeddings we will study. So as we have a vector V, this is the model which takes node use embedding and it predicts a vector V. The probability of visiting node V on random walk starting from V. Okay, this is the predicted probability. Nonlinear functions used to predict probabilities, softmax, turns real values into k probabilities, sending to 1 sigmoid basically changes the range anyways. So what is a random walk? Given a graph and starting from like a starting point, we select a neighbor of it at random and move to this neighbor, then we select a neighbor of this point at random, move to it. This becomes the random walk, the random sequence of points selected. Okay, the probability that u and v co-occur on a random walk over graph is this probability, random walk probability. Okay, so estimate probability of visiting node V on a random walk starting from node V using some random walk strategy R. Optimize these embeddings to encode this random walk strategies. Okay, so this is what that will do. So that mechanism dot product or whatever you want. Okay. Two nodes, Z I and Z G. Okay. Location is 1 there. Even though you already defined the by nodes, so this is like node embeddings. Our goal is to learn the feature. This is the neighborhood. all together into chemistry screen. Make a sampling, take whatever you want, sorry about it. It's very decent, it's a lot of noise. Okay. So how for this one, like how to optimize links in the random box strategy are. What strategy should we use? Should we use fixed length, unbiased random box, blah blah blah. So how to generalize this thing? So let's study more to it. Embed nodes to similarity network, never nodes closing feature space, we frame this as to use code and maximize likelihood optimization problem. Independent to the downstream prediction task. Okay. So use flexible bias random blocks that can trade off between local and global neighborhood goals. That is the motivate idea. Okay. So define the local macroscopic. DFS provides a macro view, and DFS provides a macro view. So you have basically a parameter P that basically means return to previous state, return parameter of then there's another parameter, whether you want to move outwards or inwards. So Q is the ratio of BFS on DFS, while P is like return probability. So that is how we make it biased. Define random walk by specifying the walk, lead travels, is not okay. So Q, the higher Q is the more is the probability it will walk away to BFS, the lower it is. The lower it will be. So assume the BFS value is large, it's like BFS upon BFS. So if its this value is large, this means that we will be doing breadth first search. If this value is small, we will be going to depth first search. Okay. So then this value is small. Low value of P is BFS like walk, low value of Q is BFS like walk. High value of P is BFS like walk, low value of high value of this thing is again BFS like walk. Because you are not returning back. Okay, so compute transition probabilities. We do our random box of length L starting from the view. Optimize using stochastic variabilism. Then we move on to know like how to embed the whole graph. So this temporary sum or average, then that is one method. Introduce a virtual node that connects to all nodes. Okay, and then you compute the embedding using these methods and then take that embedding and embed the graph. The next thing is how to compute hierarchical embeddings. There's diff tool. So we can also hypothetically cluster nodes in the graph and then some average the nodes embedding according to this cluster. So in your work, you pull this, you take this graph, then you pull again, you get graph level embedding. So this is the idea behind your GLMs. matrix factorization and node embeddings. So this is one thing. Deep is equivalent to matrix factorization of the following complex matrix expression. Random log base similarity. Nuclear can be formulated as matrix. All about this, then we can do journeys. Limitations of shallow embeddings is that there is no shared parameter between nodes. Node embeddings are independent of each other. Cannot produce out embeddings for those nodes which are not seen during training. Will not incorporate node features. Then, so to overcome this, we have to brief graph encoders, which are like multiple layers of nonlinear transformation based on graph structures. Charging our graph, we have graph convolutions. We get disembedding applied as equation function, we get disembedding them for more like this. Node classifications predict the type of given graph. But graph networks are more complex compared to what they are topologically complex and analyzing those stuff. So, you like this is basic deep learning. So we have like message passing and aggregation. These are a couple of things which we do. Main approach is like you join the decision matrix and features, lead them to a deep neural network and learn it. But the problem with this is the decision matrix is very big, and we will have like parameters equal to number of vertices for features and all, and size like more sensitive reordering and other mental steps. This stuff is good. Node reordering is a big problem. Node ordering. So you can use CMS as well, but the problem with CMS is that the real world graphs are topologically no sense of communication with them that should be quite clear. So there is no fixed notion of locality or sliding into one graph. So now that's that. So this is why we use GNS. Coming to graph neural networks. Okay. Yeah. So assume you have this graph here, and you have to compute the embedding of this node. So you take its first neighborhood, first hop neighborhood, k is equal to 1. Then you take the second hop neighborhood, k is equal to 2, and you aggregate their embeddings and you get the final number. But for that, you need to have embeddings of these nodes as well. So you, for example, you start to compute the embedding of this node, then you will have to go again. So this is like the problem where we have no information in the beginning, but we have to basically produce information by propagating information across multiple nodes. So this is a target node here. So assume like this is what are these neighborhoods? First neighborhood is B, C, and D. So you take the embedding of BCD and you aggregate them, you get the embedding of A. But embedding of B is empty, C is empty, D is empty. So you take the neighborhood as well. So you take A and C's embedding, you add it, you take A, B, C, E, F embedding, you add it, and you take A's embedding, you add it, and you get A's embedding ultimately. Okay. So basically aggregate information, you get the embedding. Model can be of arbitrary depth. Nodes have embedding at each layer, where zero embedding is the input feature. Layer K node, like layer K embedding fit information from nodes that are key hops away. Obviously, like layer 1, layer 0, this is the like initial embedding, this is layer 1. So if you keep on adding layer, it will start increasing the hops. Yeah, like aggregation is basically of multiple types. The first aggregation is like just simply average, and the second type of aggregation is that I might not over that as well. So you aggregate and then apply an notebook. That is what we do. So average and apply notebook. So what we do is we average, then apply notebook over it, and then apply nonlinearity. That's how we get the embedding at k plus 1 fluid for the initial embedding set k fluid. Okay, so the GCL embeddings are condition invariant because it doesn't matter, because like they are the shared weights. Okay. You change the order and whatever you do, like you can change the order, the embeddings. The embeddings only switch the position, but the initial values embeddings already exist in the graph. So you change the order, it doesn't matter. It's just like notation is more important, ordering is not important. So the two problems which we had in GNS was the ordering was important, new embeddings could not be introduced, and the other stuff. So they got solved using GNS and GCNs. Training is simply you are like machine learning, then there's similar nodes of similar embeddings to compute, and you will obviously get the ratio. Node similarity can be node to it, equal, struct to it, and stuff. Supervised training is nothing about you would like take a task to train the embedding. So if you don't have task, then you can simply choose the nodes are similar, you can take it 1, nodes are not similar, you can take it 0. That's how you can train unsupervised training. Okay. So this is the label vector generate based on similarity. Similarity can be used on edge connection or neighborhood. Otherwise, if you have some tasks, you can train on that task. Okay. So about that. Same aggregation parameters are shared for all nodes. Okay. So we have defined some W initial weights. The number of model parameters is some linear in D and terms of units from C nodes. Because like we are not using new parameters per node, this is just like the same model. We are just introducing it, so that's how we do it. Train on one graph, generalize the new graph. So inductive capability basically helps to create new graphs and new nodes. Yeah, this is what we used to do. GNN subsumes CNNs, obviously GNN subsumes CNNs. Because CNNs basically have a filter and they are like real aggregation over those filters. I'd say GNNs also do that. GNNs are like broader levels of CNNs. What NLP transformer is. Concepts of deep learning, level detection. Using recent and other stuff, discipline study online. Today we have like, we have shortly studied aggregation, message passing, we have graph augmentation. So we have different types of GNNs like GCN, DAT, graphs. It all depends on the type of aggregation. Okay. So the raw input graph is not the computation graph. Computation graph is different from the raw input graph. This is the computation graph. This is the input graph. Okay. So single layer of GCN has aggregation and message passing. Okay, so message computation is simply like pass the message to another layer. Nodes will aggregate this message. So aggregation can be some maps or whatever you want. issue with this type of some like aggregation, this message aggregation is information gets lost. Solution is include the previous to compute this one. So we are basically aggregation is the concatenation or summation. So GCN basically what it does is GCN is simple aggregation. Okay. But this is like your normal aggregation. So in GCN what we do is we add a weight here, multiply it by weight inside this to each layer, okay, to each of the neighborhood, then we sum it. This is what graph convolution network is. Graph Sage has something different. Graph Sage performs two-stage aggregation. Okay. So it concatenates basically. It does not sums, it concatenates previous layer to new layer. So graph, this is take the average and concatenate. Classic gaining layers, graph Sage is there. That is basically you add attention to it. Yeah. So input graph does not have any node features. So we basically assign some constant values. Standard practice is that. Okay. Now input graph is equal to convolutional graph. This is our computation, but this lacks features. Okay, so graph is too sparse, or message passing is costly. Like there are like a lot of this kind like that input graph happens to be the optimal convolutional graph for endurance. So basically what we do is we convert this input graph to have like we're not encoding vectors. So to basically augment sparse graph we add virtual nodes. So virtual node is connected to all nodes of the graph. Basically node sequence. Okay, so all they like when you have large graphs, it's very difficult to compute like so like two neighborhoods. So what we do is, so we take a random neighborhood. Every time we just change the neighborhood, so we basically use this convolutional practice. Prediction, like prediction pipeline is simple. You take prediction, whatever you want, it's like you plus the sequence. Yeah. So graph level predictions, you have to basically pool the graph. Okay, so there's a problem with that. You lose a lot of information. If you pool this thing, you cannot differentiate between the curves. Okay, because these curves are there. So how do we solve that? We are the virtual supernode as I told you. Okay. Doing the simple machine learning, the rest of classification of regression. We have message passing, classification, a lot of stuff is there. Okay, so last, how do we split the graph? So fixed split is there when there's a random split. prediction. Note 5 will affect the prediction of node 1 because of this switch, so we are not using node 5. So the option is transductive setting and another is inductive setting. Okay. Transductive setting is the input graph can be observed in all data splits. You only split the node labels. So at any time, okay, we compute embeddings using the entire graph and train using node 1 and 2 label. Okay. At prediction time, we compute embeddings using the entire graphs and validate using 3 and 4 labels. We are just splitting the node labels, not the graph. We are just moving the labels. The graph will be, the message passing will be used, but the labels of these graphs should be used. During testing, the other thing is we break the edges between the splits to get vertical graphs. Now we have 3 graphs that are independent. Node 5 will not affect our prediction of node 1 anymore. At any time we compute embeddings using graph over node 1 and 2. And train using node 1 and 2. And validation time compute using graph node over 3 and 4. Using nodes 3 and 4. So transductive settings, the data is same graph, the graphs are different. Okay. Application to this is different. So this is how the graph changes over time. So this is more graph, so this will change the labels. So graph classification and vector setting is very nice. Okay. Message passing, setting of direction. Okay. Concept of direction square. So this is all about this graph. One graph. Direction. Let's do this one as well. How expressive our GNLs. Yeah, so this is what we use for us for now, like this is what is for us. So for exam, you can study from PPT 1 to 5. That's all. And that will be the end of the session, and that will be the end of all the doubt sessions. So all the best for the exams, and study well from assignments. Okay, you can Google search for your answers, and I will be uploading the solution from assignments to the Google Drive link, where you can find the solutions to all the assignments, and then that's how you can make get your exam. All the best for that. Thank you. Let's meet next year in the same course, and most probably next semester in the other course as well. So that will be all. Thanks a lot. Take care. All the exams.